Chapter 9, Working with Exponential Functions. In this first screencast, we introduce equations of exponential functions. We begin by looking at example 9.1. Suppose a population doubles in size every 3 years. Currently, the size of the population is 600 individuals. There are two examples in this situation, time and population size. Let's let t represent the time in years since the present, and let p represent the size of the population. Let's look at part A. Determine the 3-year growth factor, R, for this population. If you recall, a growth factor is a number that you multiply a population value by in order to determine the size of the population at a time in the future. In this case, every 3 years, the population doubles in size. That means every 3 years you would multiply the population by 2 to calculate the population later on after 3 years. So in this situation, the growth factor R is 3. Let's look at part B. Assuming that the population continues to grow by this factor every 3 years, complete the following table. Well, you're told that the population starts with 600 individuals, and it doubles every 3 years. Well, the table shows 3-year periods. Notice we're going up by 3s. So at time 3, we would expect the population to have doubled, giving us 1,200 individuals. At time 6, it would have doubled again, giving us 2,400 individuals. And at time 9, it would have doubled again, giving us 4,800 individuals. Before moving on, let's take a moment and explore how we obtained these numbers. Ultimately, our goal is to produce an equation that will relate the variables t and p. So let's see if we can come up with a pattern for how these numbers were created. Well, the 1,200, we calculated that by taking 600 and multiplying that by 2. The 2,400, we found that by taking our previous year's population value and multiplying that by 2. Really, that means we're multiplying this quantity by 2 again. So that gives us 600 times 2 squared, because we multiply by another 2. To get the 4,800, we took the 2,400 and multiplied it by 2, which means we really took this quantity and multiplied it by a 2. So really what we did was we took 600 and we multiplied by 2 3 times. So as we went down the table, we just keep multiplying by an additional 2, and that's why the exponent keeps growing by 1. Let's go ahead and look at part C. Draw a scatter plot on the axes provided. Notice that on the horizontal axis we have the variable t for time represented, and the vertical axis represents the population. At time 0, there were 600 individuals. That would give us a data point right about there. At time 3, there were 1,200 individuals, which would put us right about there. At time 6, there were 2,400 individuals. That gives us a point roughly there. And at time 9 years out, we have a population of 4,800, which gives us a data point right about there. So if you examine what's happening to this population over time, notice that it seems to have an upward trend that's growing faster and faster over time. Okay, Now let's move on and look at part D. Assuming that the factor is constant, write the equation of a function that will calculate the population size at any time. Well, we were very close to creating a function equation on the last page. We found that at any time we could calculate the population by taking our 600 people, and we kept multiplying it by greater and greater powers of 2. If you recall, let's make a table here to recall what we saw on the previous page. If I make a graph or a table of t versus what the exponent was, when t was 3, our exponent was 1. When t was 6, our exponent was 2. When t was 9, our exponent was 3. So notice that regardless of what time we're talking about, our exponent is always 1/3 of the size. In other words, if I take my time and I divide it by 3, I get the exponent that goes on the 2. So if I want to calculate the size of the population at time t, the exponent will be whatever that time is divided by 3. Now let's look at part E. Your function equation above has the form y equals b times r raised to the x over delta x, where x represents the input variable and y represents the output variable. In your function, what are the values of r, b, and delta x? Well, let's make a comparison of these two equations. We have y equals b times r raised to the x over delta x. If we compare these two equations, you should be able to see that the y value is being replaced with a p, the x value is being replaced with t, the b value is 600, the r is 2, and the delta x is 3. So hopefully you can see that these two equations are exactly in the same form. You can see also that in general, the b value is always going to represent your initial amount, in this case 600. The r value is always representing the growth factor, and the delta x is always going to be representing the time period required for the quantity to grow by this factor. So this was one example of an exponential function. Example 9.2 gives us another example to consider. So let's take a look at example 9.2. In this case, a certain population is reduced by 30% every 5 years, and the current population size is 1,000. So in our last example, the population was doubling every 3 years, but in this example, it's decreasing by 30% every 5 years. Let's look at part A. Determine the 5-year decay factor, R, for this population. You may recall from earlier screencasts that the decay factor represents the percentage that's remaining, not the percentage that's lost. So in this particular example, if 30% of the population is gone, that means 70% is remaining. So our decay factor is 70%, or rather, we write it as a decimal, namely 0.70. Let's look at part B. Assuming that this population continues to decay by this factor every 5 years, complete the following table. Well, you'll notice in the table that the time increments are 5 years. In every one of these 5-year periods, the population should be reduced down to 70% of what it had been 5 years earlier. So let's see how the values in this table change. Initially, the population size was 1,000, so we're starting with 1,000 individuals. 5 years later, we should have 70% of the population remaining. We calculate that, of course, by taking our 1,000 and multiplying that by our decay factor, 0.70, and that gives us 700 individuals. To calculate the population in year 10, we take 70% of the 700 individuals. In other words, we will be multiplying the 700 by our decay factor, 0.7, and that gives us 490 individuals. To calculate the population in year 15, we take 70% of the 490 individuals. In other words, we take 490, multiply it by our decay factor in order to get the population in year 15, and that ends up being 343. Before moving on, let's do what we had done in the previous example and see if we can figure out the pattern that causes us to get these numbers. Again, our goal is to create an equation that will relate T and P, and in order to do that, we need to see a pattern in these numbers. Well, the 700, we already discussed that. You calculate the 700 by taking your initial amount and multiplying that by 0.7. To get the 490, we took the 700, in other words, we took this quantity, and we multiplied it by another 0.7. So really, we were taking 1,000 and multiplying it by 2 factors of 0.7. To calculate the population in year 15, we took the 490, in other words, this quantity, and multiplied it by another 0.7, which means we were really calculating 1,000 times 0.72 cubed. So you can see a trend or a pattern in how the population values get calculated. In all cases, we're taking the initial size and multiplying by the decay factor, and the only thing that changes is the exponent. So again, we'll figure out the equation for that in just a few minutes. Now let's go ahead and look at part C. Draw a scatter plot on the axes provided. Again, we're showing time on the horizontal axis and population on the vertical axis. At time 0, we were starting with a population of 1,000 individuals. By time 5 years, our population was down to 700 individuals, so that would give us a data point approximately there. After 10 years, we were down to 490 individuals, which would put us right about there. And after 15 years, we were down to 343 individuals, which would put us right about there. So you can see a trend in the data that it's downward and it seems to be slowing down over time. Okay, let's have a look at parts D and E. Again, assuming that the factor is constant, write the equation of a function that will calculate the population size at any time t. So let's think back to that pattern we saw. We calculate our population by starting with the 1,000 individuals, and we multiply that by factors of 0.7, and the only thing that changes is what the exponent is equal to. Let's do what we did in the last example and make a table so you can see how the exponent and the time related to each other. So here's time t and exponent. So when we went out 5 years, our exponent was 1. When we went out 10 years, our exponent was 2. And when we went out 15 years, we found that our exponent was 3. Well, notice that we can always figure out our exponent by taking whatever time we're talking about and dividing it by 5. In other words, if I divide these numbers by 5, I arrive at the correct exponent. So if I want to calculate the population at time t, the necessary exponent is going to be whatever that time is divided by 5. Let's look at part E. Your function equation above again has this same form. We saw this in the first example, we're seeing it again, where x represents the input variable, y represents the output variable. In this function, what are the values of r, b, and delta x? Well, I think you can see that b, the letter b, is being filled in with 1,000. The r in this equation is filled in with a 0.7, and the delta x in this equation is the 5. So, once again, the b value represents the initial amount of something, in this case individuals. The r is your factor. In the last example, r was a growth factor. In this example, r was a decay factor. The delta x represents the time period required to grow or decay by our factor r. In this case, decay by 70%. These examples motivate the following definition of an exponential function. An exponential function is a function whose outputs grow or decay by constant factors or percentages over equal time periods. Exponential functions have equations of this form, where x is the independent variable or the input, and y is the dependent variable or the output. The letter b represents the y-intercept or the vertical intercept. If you go back and look at our example above, b was 1,000, and you can see that 1,000 was the vertical intercept. The letter r represents the constant growth or decay factor. We saw that in our last example also. And it is the growth or decay factor for the output variable over any interval of length delta x. If you look at the example above, our population decayed by a factor of 0.7 every 5 years. So the delta x represents the interval of length over which the factor occurs. If the factor r is greater than 1, like it was in our first example where r was 2, then the function is exponentially growing. On the other hand, if r is between 0 and 1, like it was in our last example, the function is exponentially decaying, and these behaviors are depicted in the graphs below. In our first example, in this screencast, you saw a trend that looked like this. This is where the population doubled every 3 years. Anytime you have an R value, a factor larger than 1, you will see a growth that has this kind of upward trend. And the vertical intercept is always that B value. On the other hand, if you have a factor that is a fraction, say, between 0 and 1, you will have a behavior that has this downward trend like this. Again, here's the y-intercept, and it is that B value. This is referred to as exponential growth. This is referred to as exponential decay. In these last 2 examples, we practice working with exponential functions. Let's look at example 9.3. Suppose the function given by a of t equal to 15 times 0.45 to the t describes the amount of some substance given in kilograms after t weeks. Well, let's look at this equation before jumping into the problem. Is this the equation of an exponential function, first of all? So recall that an exponential function will have an equation of this form. Y equals b times r raised to the x over delta x. So the question is whether this equation here has this precise form. Well, let's see if we can match everything up. The a of t is playing the role of the y. That seems fairly clear. So the y, that's a of t in our case. The b is 15 in our case. The r is the 0.45. And the exponent is a t, but we can think of the t as t over 1, so you can see that x is the same as t, and delta x is a 1 in this particular case. So the equation that we were given is precisely in this form, and therefore it is an exponential function. Now let's look at part A. How much substance was present initially? Well, if you recall, the value B gives the initial amount of whatever you're trying to describe. In this case, that's 15. And the amount is some amount of substance that's given in kilograms. So the substance present initially is given by B, and that's 15 kilograms. Now let's look at part B. Describe the growth or decay of this substance over time. Be as detailed as possible. Well, the growth or decay of this substance would be determined by the R value. In this case, R is 0.45. So if that's the case, if R is 0.45, we can think of that as 45%. And remember that the factor is the percentage remaining. So this would imply that we've lost 55%. So 45% is remaining. That means we've lost 55%. Well, how long did it take for that to happen? That's where the delta x comes in. The delta x is 1. That's a time period, and in this example, time is measured in weeks. So over a period of 1 week, we've lost 55% of our substance. Because this is an exponential function, that means we're going to continue to lose 55% over every single 1 week period. So to describe this substance's behavior over time, we would say that it is decaying because we're losing substance. And we can say that the substance decays by 55% every 1 week. So that would give us a fairly detailed description of the decay. Now let's go ahead and see what the graph of this function would look like. So recall that the horizontal axis represents the input variable, and the input variable here is t, or time, and the vertical axis represents the output, which would be y normally, but in this case that would be a of t. So we have weeks represented on the horizontal axis, and we have kilograms remaining represented on the vertical axis. I'm going to declare this to be 5, 10, and 15. Initially we started with 15 kilograms, so we started with that amount. And let's see, I'll declare this to be 1, 2, 3 weeks. So this is 1, 2, 3 weeks. Every week we lose 55%. In other words, after a week has passed, we're down to 45% of what we had initially. So, just to give you an example, if we started with 15 kilograms, then 1 week later we should have 45% of that 15 kilograms still remaining. So if I took 45% of 15 kilograms, in other words, I take 15 kilograms and I multiply by the decay factor, I get 6.75 kilograms. So that's how much is remaining after 1 week. So on our graph, after 1 week, we should be down to 6.75, which is about here. This is an exponentially decaying function, and so its graph must have this kind of a trend to it. If we want to have a more detailed picture of our graph, then we would want to plot several more points. But we can see what the basic behavior, the basic shape of the graph looks like from just plotting 1 or 2 points. Again, every exponentially decaying function will have a graph that has this trend to it. Okay, now let's go and look at the next example, 9.4. Determine the equations of each of the following exponential functions. Okay, so every function in this example is assumed to be exponential. Let's look at part A. The outputs of this function decay by 10% over 4 unit intervals, and the graph has a vertical intercept equal to 7. So we are trying to produce the equation of this function, and we're told it's exponential, therefore it must have an equation of this form. We simply have to determine what b equals, r equals, and delta x equals. Remember that x is our input, or our independent variable, and y is our output, or our dependent variable. They will remain variable. We're not trying to determine the values of x and y. They have to stay variable. B, r, and delta x, those will be fixed. We need to determine them. Okay, B represents our initial amount, or you can think of it also as the y-intercept, or the vertical intercept. In this case, you're told that that's 7. So the B is 7. Now we need to figure out the growth or decay factor. In this case, it'll be a decay factor because you're told that the outputs are decaying by 10%. Remember that the decay factor is the percentage that's remaining, not the percentage that was lost, but the percentage that's remaining. So if the outputs have decayed by 10%, that means we've lost 10%, which means we have 90% remaining. So the decay factor would be 0.90. The delta x represents how long it takes to accomplish this level of decay, and you're told that it takes 4 units of time for this to happen. So delta x is 4. Now that we've figured out the b, the r, and the delta x, we can write down the equation for this function. Y equals 7 times 0.90 raised to the x divided by 4. Now let's have a look at the next example, B. In this case, we're given information about the graph of this function. We're told that the graph passes through the points 0, 1, and 3, 4. Well, let's start by sketching a graph of this function so that we can begin to see whether we're talking about growth or decay. The graph passes through 0, 1 and 3, 4. There. This is 4, this is 3. So 0, 1 is right about there, and 3, 4 is right about there. So you can tell already from just these 2 points that we're talking about an exponentially growing function. So the curve, the graph, is going to look something like that. Now we want to find the equation of this function. And again, every exponential function has an equation of this form. We need to figure out what b equals, r equals, and what delta x equals. Now in this case, recall that b is the vertical intercept or the y-intercept, and here you can see from the graph that the y-intercept is 1. So that means b is 1, and we need to work out what the r and the delta x equal. To this end, let's make a table of input-output pairs. We know one input-output pair is 0, 1, and another input-output pair is 3, 4. You can think of x as representing time. So think of x as representing time, and you can think of y as representing some amount, maybe some population level or some amount of substance. So this range from 0 to 3, you can think of this as a time period then. And during this time period, the amount grew from 1 to 4. So, in particular, it grew by a factor of 4 over 1. Recall that that's how you calculate a factor. You take the later amount, divide by the earlier amount to obtain your factor. So in this case, the amount grew by a factor of 4. How long did that take? Well, that's where we have to look at our time interval. X ranged from 0 to 3, so the time period was 3 units. That's the delta x. So delta x is 3 minus 0 which is 3. So r is 4, delta x is 3. Before moving on, one observation. Remember that to calculate a factor, you use division to do that. But to calculate the length of a time period, in other words, the total change in x, you use subtraction, not division. So we found the b, the r, and the delta x. So from here we should be able to write down the equation. It's y equals 1 times 4 raised to the x over 3, which we could rewrite as 4 times x over 3. Now let's look at part C. In this case, again, you're given information about the graph. So let's start by drawing a graph. Okay, so I've got some tick marks drawn in. We know that the graph passes through 110. That would be right about here. And the graph passes through 3, 4. That would be approximately there. From looking at these 2 points, you can tell the basic shape of the graph. We know it's decreasing. Also, it's exponentially decreasing, which means it's going to have a trend like this. So we are trying to determine the equation of this function. Every exponential function has an equation of this form. And again, we need to figure out the b, the r, and the delta x. In contrast with the last example, in this case we cannot tell from looking at the graph where it crosses the y-axis. We can see it's up here somewhere, but we can't tell from the information we were given. So since we don't know what the intercept is, we don't have the information to find b at this moment. We should be able to figure out r and delta x the same way we did it back in this earlier example. So let's start by making a table of values. Okay, so r, remember, is the later amount divided by the earlier amount. So that would be 4 over 10, or 4/10. Delta x is the change in x when we go from 1 to 3. The total change is 3 minus 1, which is 2. So the only thing we have left to figure out is the b. Well, what we know currently from the information we have figured out, we know that y must equal b times 0.4 raised to the x over 2. We know that much. The other thing we know is we have some input-output pairs. We know that when x is 1, y has to be 10, for example. We know when x is 3, y has to be 4, for example. So in this equation, if I replaced x with 1, I would be obligated to replace y with 10. Doing that would enable me to figure out what the b value equals. So let's do this. Let's find b. I'm going to substitute this one input-output pair into the function equation. So if I replace y with 10, I'm obligated to replace the x with a 1. So the only unknown in this equation is b. I can divide both sides by 0.4 to the 1/2. Both sides by that same quantity. On this side it cancels, and we get b by itself. b ends up equaling 10 divided by 0.4 to the 1/2. Now this is something you would want to work out on your calculator. So on your calculator you would type this in as follows. You would type 10 divided by, and then put parenthesis 0.4, and then hit your caret key, and then for the 1/2 you can type 0.5 and then parenthesis. When you calculate this, you're going to get a decimal, and it's approximately equal to 15.811. So let's see, does that make sense? B ends up being 15.811 approximately. Let's go to our graph. Remember that B represents the y-intercept. Does it seem plausible that this graph could meet the y-axis at 15.811 approximately? If we look at our graph, the y-intercept would have to be somewhere up here, and that looks like it would be near 15. So that suggests that our work was correct. So we finally have our equation for this function. The final equation is, I'll do this in black here, y equals 15.811 times 0.4 raised to the x over 2. And that's the equation for this particular function.